So you can sort of think of this matrix as a continuous function of 6 numbers, not literally.
Yes.
Sort of.
Mathematically, it is a group. You know what a group is?
I've heard of it, yes. I believe I know what it is.
Yeah. What it means is,
Like they kind of set with an operation.
yeah. So what it is it is a group. It has to contain the identity. So this defines the group. This is a Lorentz group. So this is the Lorentz group. It's all the L's that satisfy this. And it has to contain the identity, if you call this script L. So the identity is an element of script L. And if L is an element of script L, then also the inverse is element of script L. It's a Lorentz transformation. That means that L transpose G L is equal to G. And then we take the inverse of this relation. Then we get L minus 1, G is its own inverse, L transpose inverse. That is equal to G. And this is equal to L minus 1 G. The transpose of the inverse is the same as the inverse of the transpose. And now we see that actually the transpose doesn't occur in the right place. So we would like it to have in the right place. So let's write indices, alpha, beta, and beta. This is a diagonal matrix. And here, beta gamma is alpha gamma. So we can write this in this way. Let me first prove the third group theoretical relation. That is, with Lm1 and L2 is an element of the Lorentz group. That is L. Then also the product is an element. And we can show that because L1 times L2 transpose times G times L1 L2. What is that? That is L2 transpose. When you transpose, you change the order. L1 transpose G L1 times L2. So this is again G because L1 is in the Lorentz group, and then L2 is also in the Lorentz group. So the product is also in the Lorentz group. That's very important. And in fact, it is a Lie group. And a Lie group means it is a continuous group. So these are matrices. And if you change the matrix element a little bit, it is very close to the other matrix. It has numbers, and if you make one number a little bit bigger, so that's 2, 3, it's almost the same matrix. So it is a continuous group. And it is a group, and it is continuous. So it's a Lie group.
So you can sort of think of this matrix as a continuous function of 6 numbers, not literally.
Yes,
sort of.
yes. And the idea is that the following idea is that if you have a transformation, you have a Lorentz transformation, and a big one, and you do that in many small parts, say L epsilon times L epsilon. L epsilon. This is small, and by small I mean that this is very close to the identity. That you can make a big Lorentz transformations by Lorentz transformations that are very close to the identity. And this, so the idea is you only have, because you can construct any Lorentz transformations from infinitesimal ones, infinitesimally close to the identity. So the only thing what you have to study are these kind of Lorentz transformations. And we are going to solve this relation to first order in epsilon. So we are going to Taylor explain this relation. And what we use is the following thing, this to the power n, and you know what it is, that n is going to infinity.
Mm-hmm. Oh, this is e, isn't it?
That's right, that's e to the power phi. So that means from many small things that are very close to 1, you can make an exponential or X transformation. And when these are group elements, this works exactly the same. This relation is also valid when phi is a matrix. It's not only valid. So what we are going now to do is, we are going to solve this. So we have 1 plus epsilon times g transpose times g times 1 plus epsilon times g is equal to g, and is equal to, did I say, it is 1 plus, no, it should be equal to g, that's right. So then I expand it, that is g plus epsilon g transpose times g plus epsilon times g times g plus order epsilon squared. So this drops out, and this is true for all epsilon. So we see that g transpose times g plus g times g is equal to 0.
This is z transpose?
No, this is not transpose. Only this one is transpose.
So z transpose g plus z is equal to 0?
Yeah.
Okay.
And now we can put in some elements. What does that mean for the diagonal elements of G? If we do it here. If you look at the diagonal elements, so we have here GT, and now there's no summation convention. This is diagonal. This becomes alpha and plus G. I look at the alpha element of these things, and this is also diagonal, so they're all alpha, and that is equal to 0. The transpose of the diagonal elements doesn't change, so what we get then is G alpha alpha is minus G alpha alpha. So what is G alpha alpha?
The first thing comes to my mind is the 0 matrix.
This is 0,
Okay.
just 0. So these are the diagonal matrix elements. So we know the diagonals are 0. So we only have to determine the off diagonal. Do that. So if you have G alpha beta transpose, this becomes G beta beta plus, we have now the alpha beta, so alpha G alpha, the beta element. So this is diagonal, so G alpha alpha times G alpha beta. So we have, and that should be equal to 0. So this is, the transpose is G beta alpha. That is equal to, this is just a diagonal matrix with plus or minus 1. So we can multiply that. That is G alpha alpha, G alpha beta times G beta beta. For the special case of the metric we had. So what we see if you look at the matrix, when we write down this relation, when you write down this relation, what we have is if you write down the G matrix, there are 0 on the diagonals. There's G01, G02, G03. Here there is G. This is there are only 2 slots. G1, 2, G13, and G23. So and now I see when here there's when alpha is 0. So I have so this is the one alpha element. then this is the 0, 0 element, that's minus 1. And this is G 0 and 1 because beta is 1. This is the one element. So that should be symmetric. What do I get?
I see. So when neither alpha nor beta are 0, then z alpha beta is equal to z beta alpha.
I screwed up a minus sign. Oh yeah, okay, I screwed up a minus sign. This is plus. If I bring it to the other side, it becomes minus. So I screwed it up. So what we see is that when there's a 1, 0, this is minus 1, that is plus 1. So this becomes G01. The same for this one and the same for this one. Whereas when this is 1, 2 or 1, 3 or 2, 3, these are both spatial, so they are both 1, and you get a minus sign. So this is equal to G minus G1, 2. Here we get minus G1, 3, and here minus G2, 3.
And these three are equal to these three.
Yeah, that's why I give the same symbol. So now you see that this matrix has only 6 independent elements by explicit construction. And now you write this, K is 1 to 6, maybe times some numbers. Let me call them GK times GK, and these are the generators. They are called the generators, and we choose them very simple. There are 3, so this is one of the generators, 0, 1, 0, so that it is a multiple of G01 and the rest 0. So there are 3 of this type. So the next one is 0, 0, 1, 0, 1, 0, and the rest 0. And the third one is when the 1 is in the corner. And there are generators for these one. They are anti-symmetric. For example, these are called typically the name for these are called K. This K1, this is K2, and the other one is K3. And for these one, they are called S1, S2, and S3. And S1 is equal to, for this element, 0, 0, minus 1, and the rest equal to 0. S2 is 0, and then we take here the 1 and here the minus 1. 0, 0, 0, 0, 0, 0, 0. That's, the rest is 0. That's this one. And the third one is when we put the minus 1 and 1 here. And I think the typical convention is to actually change the signs. But there's a convention. That's a 0, and then we have 0, 1, 0, 0 here, 0 here, 0 here. So you can expand this matrix in terms of these 6 generators. And they are actually very important. They form what is called a Lie algebra. And the Lie algebra are commutation relations. So we have the S's, Si, Sj is epsilon ijk times sk. Do you know what epsilon means? So epsilon 1, 2, 3 is 1, and the rest is 1 or minus 1. When it's a symmetric permutation of 1, 2, 3, it is plus 1. When it's an anti-symmetric permutation of 1, 2, 3, it is minus 1. For example, epsilon 2, 1, 3 is minus 1.
Oh, I see.
And epsilon 3, 1, 2 is 1. And epsilon 1, 1, 2 is 0.
Actually, I just read about this in the textbook, but I forgot about it for a little second.
Yeah.
So
this is a very important Lie group, Lie algebra property, which is true for the generators of rotation group. And then for the other one, we have a different one, Ki, Kj, that is equal to, there's a minus sign, epsilon ijk times kk. And there's also a mixed one, Si kj, and that one is epsilon ijk, and now it becomes a kk. So that's a Lie algebra of the Lorentz group. So these are the group properties of the Lorentz group. And the important conclusion is that we only have to study infinitesimal ones. In general, for applications to general relativity, it is not that important, but to actually understand what they mean, it is important. Now, these matrices, what I said is that what you want to calculate is to make a big Lorentz transformation out of small Lorentz transformations, and you do that by exponentiation. So if you have many, say 1 plus omega, let me start with that one, with k1, and I divide this by n all the way to, I do that n times, 1 plus omega over n to the power kn. And this is all when we take n going to infinity. So these are very small, so that means that this goes to e to the power omega times k1. And what is e to the power omega k1? Then we have to, we do that by Taylor expansions, 1 plus omega k1 plus 1/2 omega squared k1 squared. And what is that? That is 1. Omega k1, that is just this matrix. Omega, we have here omega, here there's omega, here there's a 1. K1 squared, that is the identity of that two matrix. So it is 1/2 omega squared. This is 1/2 omega squared. And I want to have, a minus sign. Let me see if I can use a minus sign. Maybe I put the minus sign here. If I put a minus sign here and I Taylor expand that, I get a minus sign there. I want to have a minus sign because here I want to have a minus sign. And there are more terms. You can calculate the next term. It is minus omega to the third divided by 6. And if you, plus higher order terms. And if you do that, this becomes the cosine hyperbolic of omega. These are the first two terms of the expansion. This is the sine hyperbolic of omega. This is also the sine hyperbolic of omega. And this is the cosine hyperbolic of omega. And that's exactly what we found last time for the solution of this relation. So and this is the rapidity. So indeed you see that from this general construction you reproduce the Lorentz transformations as you originally found them.
So these are the Taylor expansions for the hyperbolic trigonometric functions?
Yes.
Okay.
Yes. If you Taylor expand that, you get this. The next term is 1 over 24 omega to the 4th. Is 4 factorial. And the next term is 1 over 6 factorial times omega to the 6th.
So it's very similar to the original expansions, but without alternation.
That's right. That's right. They are, because the cosine of omega is the cosine of I omega. What we have to do is we have to introduce tensors. I had vectors are objects with 2 indices, and they transform as, say, L mu, let me call this mu prime, L mu prime times A mu prime mu prime. So that means that each index transforms as a Lorentz transformation, and this is called a tensor. By definition, that's a tensor.
So
Think with 2 indices, and it transforms in this way. So it's a matrix too, but the reason you call it a tensor, you call it a 2 tensor, because there are 2, is the transformation properties. Always the transformation properties are essential.
So this is simply a special kind of matrix so that it obeys this equation with the Lorentz transformations?
Yes.
Okay.
And this is very important because all equations in physics are Lorentz invariant. That means if you have an equation, write down an equation. For example, this equation. So the left-hand side has to have the same transformation properties as the right-hand side. So if this is a 2 tensor, this has to be a 2 tensor. So this is the equation we want to get. This is the so-called Einstein equation. This is the Einstein tensor, and this is the energy momentum tensor. They are the same. These are the basic equations. There's some prefactor here. These are the basic equations of general relativity. Is a tensorial scalar product. So you write it as A mu of times B mu. So you can also look at it in a different way. A mu maps an element of a vector space to the real numbers. So this is an element of the reals. So you actually can consider this as an element of a vector space. So there's a different vector space. And A is an element of the so-called dual vector space. So mathematicians look at it this way, and they call this in one form. So they think of it as objects that act on map vectors to the real numbers. And sometimes, for physicists, that is not really important because we don't care too much. We want to calculate things. That goes via an action principle. So the action we call S, integral P dq. And then the equations of motion, the Newton equations, they follow from the extremum of the action. And you use that to write down an action for relativity. And for that, you derive the correct generalization of the Newton equations for relativity. And the simplest way is to do it via the action. That is the next thing I want to do.
Okay.